These are all old rules that you should be familiar with from previous years. All right? Product of two exponents or exponential expressions, quotient, power raised to a power, all that good stuff. We've been working with that all year, so that should be fine. All right, zero power, negative powers, and stuff. All right, but the important fact here, and this is the basis of a logarithm, any positive real number can be written as a power of another real number. All right, and in some cases it's really easy, and in other cases it's not. All right, or it's not as easy. All right, like for example, the first one where it says write 4 as a power of 2. Oh, yeah, look, just got that one. All right. So it's saying write 4 as a power of 2. And honestly, I figured I would take it back to this basic type of problem because you should have a great deal of familiarity with it. All right? Just going back to even elementary school. Right, so when you're multiplying or doing work with decimals, you're working with powers of 10. All right. So when they say, convert to a percent, you're multiplying by 100, which is a 10 to the second power. It's powers of 10, specifically raised to the second. All right. So when they say write 4 as a power of 2, it's saying what power would 2 have to be raised to in order to equal a result of 4. All right, so when they say write 4 as a power of 2, you would come back with hopefully 2 to the second power. All right, so 2 to the second power is that conversion. All right, so it's pretty easy. Same idea with writing 8 as a power of 2. All right, I would be saying 2 raised to what power would give me a result of 8. That would be 2 to the third power. All right. It's just simple arithmetic. It's nothing too crazy. But what they did along the way is they said, all right, well, we need a name for this because you need a name for everything apparently. But also, you're going to run into instances where maybe it's not quite as clean. All right, where you'd have something like writing 6 as a power of 2. All right, you'd say 2 to what power is equal to 6, and it's not really as clean. All right, I do know that it would be somewhere between 2 and 3. All right, because 2 to the second would give me a 4, 2 to the third would give me an 8, but beyond that, I mean, it would just be guess and check. So I would start off, just thinking about it before the concept of a logarithm was invented or discovered or created. I would say, all right, well, it's not 2 to the second. It's not 2 to the third. So I might say 2 to the 2.5. All right, that's pretty close. It's not close enough, but it's close. Maybe 2.7, that's too much. 2.6, a little too much. 2.59, a smidge too much. 2.58, a smidge too little. So maybe like 2.585, a teensy tiny smidge too much. So maybe 0.584, smidge too little. So maybe 0.58, well, it's not 4. 4 is too little, 5 is too much. So split the difference, go halfway, still a little too little. Maybe go to 6, still too little. 7, 8, 9. But if I bring this up to 5, it's too much. So I'd leave it at 4.9 and go out another decimal place. Maybe a 5. Maybe I'll just try 9s. Too much. 8, still too much. 7, too much. 6, too little. 6.1, not enough. 6.5, too much. 6.4, still too much. 6.3, just a smidge too much. 6.2, too little. Throw a 5 on, still too little, maybe a 6. Too much, so maybe like a 5.5. Too much. 4, 3, 2, oh man, so close. 1, So maybe like 4, 9 even. No, 5, got to go higher. So maybe 5, 0, 5. Not quite. 4, 3, 2, 1. Oh, like right there. And it's fun. It's therapeutic, I guess. Can't imagine doing this like too many times, but oh, the 7 is too little, the 8's too much. So split the difference, throw in a 7, 5, 7, 4, oh, 7, 1. Oh, too little. 7. Oh, there we go. Got it. All right, so could do that. So that's going to be 2 to the 2.584962500072. Yeah, we got our answer. That wasn't too bad. I actually started teaching logarithms like this, like maybe 10, 15 years ago, because, and I probably shouldn't admit this, but I forgot to make a lesson for that day, and I was like, all right, I need to kill 40 minutes. So I just did like 2 or 3 problems like this. There goes the class period. It was fun. Students loved it. So that, writing 5 as a power of 2. All right, we could just do that again. Before you know it, the whole week will be over. It'll be great. We would not have learned any calculus. That would be unfortunate, but, So 2 to the something power, you got to imagine it's going to be a fairly lengthy decimal, is going to be equal to 5. All right, we could go through this process again. However, we don't really want to have to do that, as we know. All right, so what happened along the way, I believe guy's name was John Napier. He came across a more streamlined way of coming up with these powers. It started off with what they call the Table of Logarithms. All right, the Table of Logarithms was actually the result of somebody sitting down and doing all these computations and then just making a table, a reference table for other people to use. Right? So when you type in something like log of 5, it's not that the calculator's computing it on the spot, it's referencing that value. All right? It's determining that value based off of what's stored in its programming. All right? So what's happening here is when I say write 6 as a power of 2, I'm saying what is the logarithm with a base two of 6? All right, what is the logarithm with a base of 2, with a base 2 of 6? All right, so that became the standard notation, or the standard way of thinking about it, because the logarithm part of it, it's a logical algorithm. That's all it really refers to. All right. So if you break it down into the roots, all right. So algorithm is a set of procedures. All right. So that's why people, when you go into an algebra class, very often the reaction is, this isn't math. And we're like, well, no, it's algebra. All right, well, what's algebra? It's the ability to follow a series of procedures. All right, so that could take on a variety of different forms. All right, so here we're following a logical algorithm, which should be the basis of all algorithms, but for the purpose of determining the result, the exponent that it would take to get from a 2 to a 6. All right. So when I write this as a log base 2 of 6, that notation, all it's really asking is, what would I have to raise this number to in order to equal this number? All right? That's really all it's asking. It's just asking it in the most roundabout way possible, the weirdest way possible. So when I say write 5 as a power of 2, I could also say, what is the log base 2 of 5? All right. So what is the log base 2 of 5? Now, that result is going to be my exponent. All right. So log base 2 of 5 is actually the answer. When they say write 5 as a power of 2, 2 raised to the log base 2 of 5 is actually the final answer. I mean, you could put it in decimal form if you want, or at least the exponent, but that's all you'd have to do, right? So just going back a sec, in Desmos, if you go into function under miscellaneous, you should see an option for a log. Well, there's actually 3 options. One is the natural log, or log natural. All right. That's actually where it comes from. The ordinary common log, which is a base 10 logarithm, and then a log with a little subscript of a. That allows you to put in any base you want. All right. So if I put in 2 as the base, and then put in a 6, it brings back that decimal that we came up with trial and error before. All right. So now I could just figure that out for something like number 4. Log base 2 of 5 would be that disgusting decimal. All right. Now, if I want to verify that the left side of this equation is going to give me, in fact, the number 5, because it's kind of weird to look at. You say 2 raised to the log base 2 of 5, and you're like, somehow that's going to equal the 5? I'm not buying that. All right. So what you would do in Desmos is put in 2, raise it to the power of log base 2 of 5. And you'll see it results in the value of 5. All right. And that actually brings us to a nice property of logarithms. All right. So it gives us a nice rule here where we can now say that if I have some coefficient a, or some value a, and I raise it to the power of a log with that same base. All right, you notice how the 2 here is the same as the 2 there. All right, same idea here. This a is the same as that a. And I could put in whatever value I want here. I'll call it c. The result is just going to be c. Well, actually, let's go with b. Only because I just looked at what I put for number 8, which is really that same idea. All right. So what I can do here in Desmos is populate this, or use the put the rule in and populate it with a and b values. All right. So I would say a raised to the natural log. We'll get to natural log in a second. Log base a of b. Create some sliders. And verify that this is going to be a true sentence for all a and b, or all positive a. All right, so throw in some values here, like for example a 4 and a 6. I can move my a wherever I want, and that b is going to stay put at the 6. All right. So whatever that b value is, that's going to be my answer, regardless of what the a value is. Except where you get some undefined values if you try to go for a negative base. That's not going to fly. All right. And that's the reality there is you can't take a positive number, a negative number, raise it to a power, and end up, so you can't take a negative number, raise it to a positive power, and end up with a negative answer. All right. You can't take a negative number, raise it to a negative power, and end up with a negative answer. All right. It'll always end up being positive. I feel like I said that backwards. Negative. I'll come back to that. I think I just had a brain cramp. But anyway, writing 8 as a power of 3, very easy now. So 3 to the log base 3 of 8 is going to be equal to 8. All right. But then we get into base e. All right, writing as a power of e. So this would be the same as saying e raised to some number would give us a result of 8. All right. So we could go the trial and error route, but if we know that e is some number, all right, approximately 2.718, then the rules would still apply. All right, the rules that we just came up with would still apply. All right, so I would just write this as e raised to the log base e of 8. All right. But that log base e is the definition of a natural log. All right. So this is the same as saying e to the ln of e. E to the ln of 8 is going to be equal to 8. And that is also something we could test out on Desmos. So I would say e raised to the ln of 8 gives a result of 8. All right. If I do it for some value b, the result here is 6, but that's because that's what b is set to. If I have b set to 2, the result will be equal to 2. All right, so writing b as a power of e to the log base e of b would be equal to b, which is the same as saying e to ln of b is equal to b. All right, and this is the foundation of one of our log rules that we came up with last week. The idea that any number can be written as a power of e. All right. So if I needed to take the number 2, for example, and write it as a power of e, I can call it e to the ln of 2. All right. So that allows us to use our log rules, or natural log rules, for finding derivatives. All right. It takes away a lot of the guesswork there. And that I think was a lot of the cause for concern last week when people were having difficulty understanding that transition. It was probably because of this concept right here. All right, so that was the quote unquote gap in your learning. All right, so I'll write it again though. So for example, let's say you had I think it was something like 2 to the x power, something like that. 2 to the x. And I want to write it as a power of e. We now know that 2 can be replaced with an e to the ln of 2. That they're equivalent. So instead of having a 2 to the x, we would have e to the ln of 2 raised to the x. All right. And again, go to Desmos if you're not sure. You know, if you think something's a rule, but you're not 100% sure, test it out and see if it's legit. So e raised to the ln. And by the way, if you have trouble finding rules or functions in Desmos, like you click on the function key, then go to miscellaneous, whatever. You could also just type it in. Right? You type in ln. It starts off in italics, but then it kicks over to ordinary font. Whenever it does that, whenever it kicks over to ordinary font, that's Desmos indicating that it recognizes that as a relationship. So then you're good to go. Right? Same thing with like sign. You type in SI, it thinks you're putting in some coefficients, but then when you type in the N, it kicks it over to ordinary font, so it now is indicating to you that it recognizes what you just typed in. So ln, e to the ln of 2 gives you a result of 2, so we know that they're equivalent. All right. So then I could say e to the ln of 2 times x. These would all be equivalent. All right. And again, you're not 100% sure, type it in as a function. Y equals 2 raised to the x power. Y equals e raised to the ln of 2 times x power. Oops. I'll put the x in front. Makes it a little cleaner. But you can see that they're plotting the same graph. All right, same graph. Same graph, same function. All right. So that was a little crash course on the origin story behind logs. But we also needed to review things like converting from exponential to log form and also properties of logs. Right? Because it's one thing to numerically determine the value of a log. I mean, you could have, if I told you find the log of 12, you didn't need this whole lesson in order to figure that out. You just type it in. All right. Hopefully you're finding some value in what I'm sharing with you, because honestly, I made it all the way to, I would say, probably my 5th year of teaching before I truly understood what a logarithm was. All right, so that puts things in perspective. I was in my mid-20s before I fully understood it. All right, I didn't even understand why functions were important until I was like in my 30s. All right, because it was all just stuff that you did, like. You verified something was a function using the vertical line test. Why? Because it freaking told you to. That's why you do it. Right? You're gonna solve a log equation. Why? Because they told you to. Right? We're gonna find derivative of a log equation. Why? I already said it. All right. But the whole origin story behind this, it should have some value, because if you think about it, the real world doesn't work in straight lines. The real world is curved, right? We have a requirement for other types of functions, and exponential relationships are the basis of growth and decay. Right? You can't really talk about the rate of growth without really getting into exponentials. Right? I even think of something as simple as, like you take medicine, and I think I gave this example before, but like, how do you know? Like it says, take this medicine once every 4 hours. Where are you getting the 4 hours from? Well, it's a logarithmic or an exponential relationship, depending on how you look at it. All right, it's the decay of the active ingredient of the medicine in your bloodstream over time. All right. Now, is it ever going to completely dissipate? Maybe, maybe not. Depends on the medicine. But they get into things like half-life. If you take like a blood test to detect the presence of a drug in your system, there's certain drugs that'll stay in your system for only like a couple of days, some that'll stay in for a couple of hours, and then there's some that'll stay in your system for weeks and be detectable. All right, so how does that happen? Well, it happens because it levels off. It doesn't decline and then just disappear. There's trace amounts of it because it's logarithmic in nature, all right? So, or exponential, again, depending on how you're looking at it, all right? So, computing logs, not difficult, but getting a log equation or expression into a form where it is easily computable, that's really where we're going to take this. All right, because like for example, the first and second ones, those just get popped right in. All right, 3 raised to what power is equal to 42? I mean, that's just saying the log with a base of 3 of 42. So that's approximately, they said 4 decimal places, so 3.4022. And again, all that number is telling us is what I'd have to take the number 3 and raise it to in order to get a result of 42. All right. 3 to the third power would give me a 27. 3 to the fourth power would give me an 81. So it makes sense that 42 would be somewhere in between. All right. So 0.5, I'll type that in as 0.5, and then a 5. Now this one, interesting result. All right. So we get a negative result for a log, which is telling us that I can take that 1/2 and raise it to a negative power and still get a positive result. All right. The thing is, we're not going to be working, you're not going to have a negative base for a logarithm. So we're not looking at an instance where I would take this 1/2 and raise it to a power and get a negative result. All right, because if I'm starting off with something that's positive, raising it to any power, whether that power is positive or negative, is still going to give me a positive result. All right, that's what I was trying to say before, but I did not do a good job at that. All right, so anyway, properties of logs, you have all of these different things, and you know, it's easily confused with calculus because we've already learned a power rule for calculus. So we're going to go back and review a power rule for logarithms. We're also, for calculus, going to learn product and quotient rules. Of course, there are product and quotient rules for logarithms as well. So we got to keep these things straight in our mind. But in terms of just getting it into a simpler logarithmic form, there's really a significant value in that, because if I tell you, for example, and I'll just keep it simple here, and I'll throw it off on the side just so you get a sense of where this is going. If I say, for example, find the derivative of the function f of x is equal to the log, I'll say natural log of 2x squared over x plus 3. All right. And we'll just hang on to that example for a minute. And I'll show you why these properties of logs are going to be valuable for us. All right. So just going back to number 3, we can apply any of these rules as needed. I see here that I have a product of x to the 5th and a y. All right, so that would tell me that I would want to apply the product rule. All right, so log base b of x to the 5th expands out. So log base b of x to the 5th y expands out to log base b of x to the 5th plus log base b of y. All right. So then we could apply the power rule. The power rule takes that 5 and makes it a coefficient. The power rule has to come second here. It has to happen after the product rule. And the reason why is that power of 5 only applies to the x. So it isn't a matter of me saying, oh, let me just take that 5 and move it to the front of the log. It's not relevant to the y. So I'd have to split up the log first before making that move. But the simpler log form here would be 5 log base b of x plus log base b of y. Now it's kind of weird to think of this as simpler because it definitely looks more complicated, but they're logs of simpler terms. All right? The argument contained within the logarithm is much simpler than what we started with. All right? We took an order 6 logarithm, which is just saying that the high power contained within the logarithm was power of 6, because you got x to the 5th and a y to the 1st. Put it together, that's giving you a power of 6. All right? We just took that and broke it down so that the highest power contained within any logarithm is a power of 1. All right, so we made the arguments contained within the logarithms linear rather than high-order polynomials. I mean, that's a win, right? Like number 4, I see a power of 5, power of 3, and a power of 1/2. All right, so we have high-order polynomials and a root function, and it's a rational root function because it's part of a denominator, right? Assuming that these are variables and not just simple coefficients, all right? But we could split this up and clean it up and end up with something much nicer, all right? So we'd start off with the division, which would give us a little quotient rule. So log base b of m to the 5th, n to the 3rd, minus log base b, I'm going to write that p as p to the 1/2 power. That m to the 5th, n to the 3rd, that would be product rule, splits up to log base b of m to the 5th plus log base b of n to the 3rd, minus, we still have that log base b of p to the 1/2. And then the last step here would be to take all of these powers and make them coefficients by applying the power rule. Just 3 times. All right, so 5 log base b of m plus 3 log base b of n minus 1/2 log base b of p. All right. So much cleaner. And again, the applications are pretty important for us because we have this, like this function that I just made up on the fly here. But we're going to have to take derivatives of logarithms. I mean, we know how to take the derivatives of involving exponentials, but taking the derivatives involving logarithms is only going to be as difficult as what is contained within the logarithm. All right? If it's a simple function within the log, then it's going to be an easy process. If it's a really complicated function within the logarithm, then it's going to be a disaster. All right? So fortunately, we have rules for logs that allow us to take something really complicated and make it much nicer. All right? So what I would do here is look at this and say, all right, I got f of x is equal to the natural log of 2x squared minus the natural log of x plus 3. I see a product here of 2 and x squared. So that tells me I could take my f of x and make it equal to ln of 2 plus ln of x squared minus, we still have that other part there, and then we could apply our power rule here to get a revised function, ln of 2 plus 2 ln of x minus ln of x plus 3. Now, without getting into the process of finding a derivative of a logarithm, because we don't have time for that today, I can tell you that this is going to be a whole lot easier to do than the original function. All right? But again, you want to make sure that you're in good shape in terms of what you have now being equivalent to what you started with. So what I would do is type in each of them and make sure that they they jive, because you don't want to be in a situation where you did all that work and you end up with a function that's not equivalent. It's a good looking function, by the way. Look at that. So a good thing about composite functions, like I was saying last week, when you take two functions and splice them together, it embodies characteristics of the individual functions themselves. So you have a graph that has characteristics of a log function. You see the part where it increases sharply and then levels off. But then it has concepts of rational functions mixed in there, so you get your asymptotes and things like that. It's just cool. It's even cooler when you find out what a lot of this stuff is used for. Like there's some functions that we're going to learn about called Bezier curves. I'm 99% sure that it's not pronounced that, but it's the foundation of like typesetting, like all the fonts that we use, like when we're typing stuff, and also the curvature of cars. It actually started off with that. The Bezier curves started off as the solution to a problem by somebody named Bezier to generate a quick and easy way to determine the different shapes that they can make cars to make them more aerodynamic, basically, cut through the wind a little easier. Right? But he wanted to be able to modify the function easily, and so that type of function was created. Right? And we'll talk about that as we go, but it has a lot of basis in the stuff that we talk about here. But you can see these two graphs are equivalent, right? Or at least part of it, anyway. And that's really all that matters. All right, so that's your crash course on logs. There's some log equations here, but we don't really need that right away. We can come back